Today, I'm going to talk about performance analysis of GPU-accelerated applications with HPCToolkit. So I'll start with an introduction to the HPCToolkit performance tools and give an overview of their components and their workflow. We've worked on making the tools easy to use, and I'll show you how to use the graphical user interface to look at your performance data. I'll spend a fair bit of time doing that in the context of the talk, showing you some canned slides and also a live demo. And then there's an opportunity for some hands-on. And so I know that in the previous session, Samir was showing you how to use this cloud-based desktop solution that they have at the University of Oregon. And so we can leverage that for using the HPCToolkit graphical user interface. And so if you already brought that up, you can bring up, if you shut it down, you can bring it up again so that we can use it during this session. Or on slide 69, there's some instructions for how to download a copy of the HPC Viewer graphical user interface onto your laptop. And then we have a remote interface that'll allow you to access performance data. So you may want to take a look at that and maybe download some software onto your laptop while I'm talking. The other option is that you can run the graphical user interface directly on Aurora and display on your laptop or desktop using X11. And so if you have an X11 capable desktop, then that's a direct solution that doesn't require either Samir's browser-based VNC or the remote server that is described on slide 69. So let's get into it. So today I'm going to be talking about the HPCToolkit performance tools. These were principally developed by my group at Rice University. They're now a Linux Foundation property. We've joined the High Performance Software Foundation last year, along with a number of other DOE-sponsored projects. And so HPCToolkit can collect profiles and traces of unmodified CPU and GPU accelerated applications. So Samir was talking about sort of similar capabilities that Tau has for doing that sort of thing. With HPCToolkit, you can understand where an application spends its time and why. And so we collect call path profiles that associate metrics with application source code context, with full calling context. And you'll see what I mean by that in a few minutes. And then we also have ability to analyze instruction level performance within GPU kernels and attribute it to your source code. And so today we can do that, the instruction level analysis on NVIDIA GPUs and the capabilities on AMD GPUs and Intel GPUs for instruction level measurement are working in-house, and we're working to put them in the newest release, which we hope to have available before the workshop. So the other thing you can do with HPCToolkit is you can collect hierarchical traces that help you understand the dynamics of your execution and see how the behavior evolves over time. And like Tau, HPCToolkit works on lots of things. And so for large-scale applications, you'll typically have a programming model within a node and then something across nodes. And so MPI is the most common thing across nodes, but there's others. Within nodes, there's OpenMP, Cocos, Raja, HIP, DPC++, SYCL, CUDA, OpenACC, the Python-based frameworks. And so HPCToolkit is capable of working with them all. And in terms of the hardware it supports, we support x86 Power and ARM CPUs and NVIDIA, AMD, and Intel GPUs. So why would you use HPCToolkit? Well, you want to measure and analyze the performance of GPU accelerated applications, and it's easy to profile unmodified application binaries. You can build your software the way that you're familiar with. HPCToolkit generally has low overhead measurement. It's informative. It can tell you where your application spends its time and why. The call path profiles associate metrics with context in your application source code, and not just functions, but also at the loop nest level, at the line level. You can see inline functions, And so that's really a unique capability of HPCToolkit compared to other tools. So you can also collect optionally these hierarchical traces that help you understand the behavior over time. So we designed HPCToolkit for a broad audience, for application developers, framework developers, and runtime and tool developers like ourselves. So we actually use HPCToolkit to tune HPCToolkit's capabilities, because HPCToolkit is its measurement system and then its postmortem analysis system. They're parallel programs. And so we tune our parallel programs using our own tools. And so unlike vendor tools, ours work with a wide range of CPUs and GPUs. So how does HPCToolkit differ from vendor tools? So on NVIDIA GPUs, there's NVIDIA Nsight Systems and Nsight Compute. And so Nsight Systems does tracing of CPU and GPU streams, and it analyzes traces when you open them with a GUI. And so the traces can be huge and slow to analyze, and it's really designed for measurement and analysis within a node. You can open up more data than on just a single node, but it's pretty slow to do that. Nsight Compute is meant for like diving down and looking within a kernel, and it gives you detailed measurements of kernels with hardware counters on the GPU and replaying the GPU kernels in order to be able to collect detailed measurements. The measurement is very slow because they do the measurement in such detail. And if you have kernels that call helper functions, all you see are sort of like a flat view. Like I was in some function F, and you don't know how you got to F. And so it may have been A calls B calls C calls D calls F in the GPU kernel, and you don't see any of that with Nsight Compute. With our tools within a kernel, you can see the nested functions, the call chains. You can also see inline code and loop nests. And so vTune and Omnitrace from AMD, they're less capable than NVIDIA's tools, but they're also designed for use on a single node. HPCToolkit supports measurement analysis on a single node, but also like across a whole exascale system. So we've collected data on tens of thousands of MPI ranks and thousands of GPUs or GPU tiles. And so I'll talk a little bit more about that as we go through and show you some examples of successes measuring and analyzing things at scale. So how does HPCToolkit work? So the workflow is as follows. There's 4 tools in our system. There's HPC Run, which profiles execution on CPUs and GPUs. HPC Struct, which is for analyzing binaries to recover mappings to source code. HPC Prof, which will combine information about the mappings between machine instructions and source code with profiles and traces. And then HPC Viewer, which presents the profile and trace view. So let's look at how that works. So you build and compile your code the way that you normally do. And so one thing that you might not be doing today is you might not be using a -G option. So the compilers by default won't collect any information about the mappings between machine instructions and source code. So to use HPCToolkit most effectively, and in fact to use any performance tool effectively, if you want to see data in with detailed attribution below the function level, if you want to see it attributed to statements or loops or inline code, then you have to give a -G option. And so with NVIDIA's tools, there's a -line info option that has to be passed when you're compiling for the GPUs. And so generally we say that you don't have to touch your make files, but if you're not already having the compilers collect line map information, then you might have to just tuck that in order to get the most out of our tools. So then HPC Run collects call path profiles and optionally traces of interest. And I'll explain what I mean by a call path profile in a moment. And so what it outputs are these profile files and trace files. So what does it do? Well, it's measuring both CPU and GPU accelerated applications. And so what we're doing is we're sampling using Linux timers and hardware counter overflows on the CPU. So conceptually, we can say, I want to know where I'm spending my time. And so when you launch something with HPCToolkit, it will say, say 1,000 times a second, it will interrupt your application on each thread and say, where am I now? And it'll say, well, you're in some function, main calls A calls B. Okay, and you find that you're in a sample in this context, and so we'll charge some of that thousandth of a second of time to the context that you're in. And similarly, you can use hardware counters to interrupt your program to say every million cache misses or every 10 million instructions executed, give me an overflow, or give me an interrupt whenever you've stalled on memory for more than 1,000 or more than a million times. So you arrange to have these interrupts driven by either time or hardware counter overflows. We get callbacks from the vendor GPU monitoring infrastructures when GPU operations are launched and sometimes when they're completed. We get an event stream for GPU operations that says that there was a kernel launch, there was a memory copy launched, there was a mem set performed on the GPU. And then also we were able to talk, my group personally was able to talk NVIDIA into adding support for instruction level performance monitoring in their GPUs. And so they support instruction level performance monitoring with PC sampling. And what this means is that the same way that we do sampling on the CPU, we can do sampling on the GPU as well and associate performance and cost with individual machine instructions in your kernels. And we also, as part of the exascale computing project, got AMD to add support for instruction level performance monitoring to their GPU hardware. That's first available in the MI300 series. There is support for PC sampling on Frontier, but that is done entirely in software. And then in the Ponte Vecchio GPUs that are in Aurora, Intel also added support with our urging. So on the Intel GPUs, we also support binary instrumentation for some fine-grained measurement and understanding your usage of SIMD lanes and things like that. So what we do in HPCToolkit is whenever a timer or hardware counter overflows, we're going to get an interrupt, and we get interrupted at some instruction. And let's say we're in some routine C, which was called from B, which was called from A, which was called from main. And so we'll collect this call chain. And then over time, we're going to collect a series of call chains at different points in the program, and those get assembled into a tree. And so conceptually, there's something like main up at the top, and then you might have a subtree that represents initialization, a subtree that represents solve, another subtree that represents finalization. And then there's costs associated with each of the leaves and the interior nodes for cache misses or time spent in the GPU kernel, or time spent stalled in GPU instructions. And all of these are metrics, and you can think of them as just costs that are annotations on nodes in a tree. And so when a GPU kernel is launched or a GPU operation is launched, we're similarly going to collect the call path to find out where you were when you launched the code. So we'll know that you were in routine C when called from B, when called from A, when called from main, when you launched the kernel matrix multiply on the GPU. So to use HPC run to measure CPU or GPU activity, it's pretty simple. You'll say HPC run -E saying I have an event I want to measure. And so here we'll say GPU, and you'll tell it what kind of GPU. And so that's NVIDIA, AMD, OpenCL, or level 0. We're going to change these to CUDA and ROCm, but this is the way it is now. We can collect instruction level measurements on NVIDIA GPUs. You can say GPU equals NVIDIA, comma PC, and this means that we're collecting the PC samples at the level of individual instructions. If you want to do profiling and tracing, so here I was just saying these are just events to say, like, watch as the GPU operations are being launched and record them in profiles. If you want to see traces, then you give this -TT option. There's a -T option and a TT option. The -T option says, I want to trace the activity on the GPUs. I want to trace the activity on the CPUs. The -TT says, every time you launch a GPU kernel, note on the CPU what your calling context was as well. Otherwise, we might be sampling much slower on the CPU than the frequency with which we're launching GPU kernels. So, so here we're saying that I want to sample using CPU time on the CPU, and I want to trace the activities on the GPU. And actually, I'm going to measure the activities on the GPU, and then I'm going to trace them both. And here I just use CPU time as an example. I could use cache misses or cycles or instruction stalls. There's a lot of things that you can do. And then if you're launching on a parallel system like Polaris or Aurora, you might be launching your application using MPI exec. And so you give MPI all of its arguments. And then instead of having your application, you'll say HPC run with its arguments. And then you'll have the application and its arguments next. And so conceptually, the MPI exec is launching HPC run, and HPC run is then launching your application. And so that's it for measurement. Basically, there's a couple of knobs where you specify the things that you want to collect here, but it's all done with the command line arguments. So the next thing is HPC struct. So your application is a binary, and it's been compiled into machine code, and it has source line information that was collected by the compiler when you specify -G. And so what HPC struct does is it analyzes your program structure, and it recovers information about the mapping between machine instructions and source code. When you launch an application with HPC run, and binaries are loaded into the GPU, HPC run records the binaries that were loaded into the GPU, and those are similarly analyzed with HPC struct. And so you can imagine that when you launch an application, it might have 100 shared libraries. There's a bunch of GPU binaries. What happens is all of those things get stuck in the measurement directory along with profiles and traces. And so then you just apply HPC struct onto the measurement directory, and it will analyze whatever binaries were involved in your execution, and then write up program structure information that says how the machine code in your CPU code maps to the instructions that are running on the CPU, and how the GPU instructions map back to the source code that was compiled for them. So you apply HPC struct to your measurement directory. There's only one option, which is one significant option, which is GPU CFG yes. And this is needed only for NVIDIA GPUs, where we're collecting the PC sampling data. So if you want to actually attribute to loop nests in the GPU, then we actually have to analyze the control flow inside the GPU kernels. With NVIDIA's tooling, they unfortunately didn't give us an API for it, and so we have to use some command line tools under the hood. We're using command line tools to dump it in ASCII and then parse it. That's expensive, and so you only turn this on when you want it. So what HPC struct does is it recovers the program structure information, as I said, which is the files that the machine code relates to, the functions, inline templates or functions, loops, outlined OpenMP code, and your source lines. And then in parallel, we're going to analyze all the CPU and GPU binaries that were measured by HPCToolkit. And so we'll use about half the threads that are available on whatever you're running on. So if you're running on a compute node, we'll use about half the threads on the compute node. And we'll typically analyze large application binaries that are 100 megabytes or more with 16 threads. And then for smaller things, we'll just say, well, we're going to launch them all with 2 threads each. And so, so we're either analyzing with larger scale parallelism, large binaries, or with smaller scale parallelism, many binaries at once. And then we cache the results, because there's no reason to compute the mapping between machine code and the source code repeatedly for libm and libc and libmpi and all sorts of other things. So if you're in a profile and analysis loop, then we're only analyzing the things that have changed. Everything else just gets cached. So that makes it faster. So then the the third step is using HPC-Prof MPI. So that will take the profiles and the traces that are in the measurement directory and the program structure, which has also been, it's when you analyze with HPC Struct, it also puts the results in the measurement directory. And so you just apply HPC-Prof to the measurement directory, and it combines the profiles, traces, and the program structure to give you your resulting database. So you apply HPC-Prof to the measurement directory, and this will analyze data from modest executions with multi-threading. When I say modest, I mean you can analyze data from collected on 100 nodes, and HPC-Prof will use a single node, and it will run a thread on every core and every hardware thread that's available on the node. So it's using multi-threaded parallelism. If you actually collected data at very large scale, where maybe like the entire scale of Aurora, then if you have hundreds of thousands of profiles and tens of thousands of GPU traces, then you might want to use our HPC-Prof MPI. Now, the MPI does not mean that it's analyzing an MPI program. This means that this is an MPI program for analyzing performance data. And so you launch it like you would any other parallel program. And so here I'm just showing you launch it on one node with 128 threads, but you can also launch it on a dozen or 50 nodes. You probably don't want a huge number of nodes because it's using large-scale multi-threading within the nodes. And this is only for analyzing data at very large scale. Otherwise, HPC-Prof is very capable with its multi-threading. So that produces a database file, and then we look at that with our user interface. So here is a code-centric analysis view of the user interface. And so when you first open it up, it's going to open up, well, it's not going to be open in such detail, but this is showing after I've clicked on something in the navigation pane, it opened up the source code pane. So we have a source code pane, a navigation pane, and a metric pane. And the metric pane might have 100 metrics in it. And here is just showing a few. And you control what's displayed, and you can scroll them side to side and focus on what you want. So there's some view controls. You can see a top-down view where we're looking down the call stack to see things that main called and things that they called. There's a bottom-up view where if something like, let's say, memcopy gets called in lots of places in your application, and you want to know where all the GPU memory copies are and how much time is spent in the GPU memory copies, then you can use the bottom-up view, and it will tell you how much time is spent in the memory copies, and then you can see, looking up the call chains, where all those memory copies came from. And then there's a flat view that lets you see the code in detail. So in the navigation pane, one of the things that comes out of using HPC Struct, the binary analyzer, is that you get a very detailed view. So not only is this a call chain, like main calls A calls B, we see function calls in full context. We see inline procedures. The inline procedures have an I in square brackets around them. You see inline templates. So Raja, here's a call to Raja. With Cocos, you had templates as well. And those are also marked with an I. And we're recovering all of this information about inline code using HPC Struct. And it doesn't cost anything during the data collection. This is all just information that we knit together in our postmortem analysis. You get outlined OpenMP loops and then other loops in the CPU or in the GPU as well. So one thing that with the code-centric view where we're looking at profiles collapse out the time dimension. And so we also have support for tracing where we're looking at things over time. Our tracing is very different from other tools. And so what we're doing is at some time t, we're taking a sample where either we were interrupted on the CPU or we launched a GPU operation, and we unwound the call stack to take our cost and attribute it to a calling context. And we do that at time t. And so if we're just sampling on the CPU, then at time t, we're going to collect a call chain. Time t plus delta t, t plus 2 delta t, we're going to collect these individual call chains. And so we do this over time for a thread, and then for every thread and MPI rank in the system, and we do this for the GPU streams as well. And so what this does is it enables you to look at the behavior over time at multiple levels. And so conceptually, you have a visibility plane where if you raise it all the way up at the top, then you'll see that everybody is in main or things main calls. And then you look a little bit lower, then maybe the next level is something like run. Okay, and then if you go down to the third level, then maybe you see like an initialization and then some sort of solve phase. And if you drop the visibility plane down to the next level, then you'll see details of what's happening inside the solve. And so what this enables you to do is to have like a top-down view of the execution and understand what's going on. So what does this look like in practice? So here's a view from an MPI-only application. But it works the same way for CPU and GPU accelerated applications. So on the vertical axis, you have MPI ranks, OpenMP threads, and GPU streams. On the horizontal axis, you have time flowing from left to right. On the bottom, you have a depth view that is showing the calling context history of a thread or GPU stream. So the cursor here says that it is in rank 93 at 86 seconds into the execution. And so on rank 93, this is showing us the history of the call stack. And so here we can see that the call stack was constant for some period of time, is probably, waiting in a synchronization event or waiting for a barrier. And so it was doing the same thing for a longer time, whereas when it's computing, there's like lots of different changes in activity where it's calling and returning from various functions. So the cursor here shows like the point that you've selected where you're interested in finding out what was going on there. So if I want to know what this green is, I can just click over here and move the cursor there. And then when I put the cursor in a place, then it will tell me what the full calling context is at that place. And so right now I'm looking at a particular depth in the call chain. And so this is I'm looking at a depth of 13 layers deep. And what this is showing is what everybody's doing sort of 13 levels down in their call chains. And if you don't have 13 levels here, it has fewer. And so if I'm trying to visualize what's happening at something that has only, say, depth 8, if I look at it at a deeper depth, we always just see the bottom level. So you never sort of fall off the end. And then in the bottom corner, there's a mini map, and that shows you the fraction of the execution that we're looking at. So we're looking at this white stripe and where the box represents the whole execution. So I should mention that the color at this point comes from the color of the procedure at the selected depth. And so what you get to see is what everybody is doing. And if you want to, and this is not a legend for the display. This is just telling me what the calling context is for that point. And each procedure has a color associated with it. And so if I want to know what this green color means, I click over here and then see what the green color is at the selected call depth. And so that would tell me that I'm waiting at a barrier for these late arriving threads to arrive. And then there's sort of a sharp contour as everybody switches into the next phase of the application after everybody arrives. So that's what this view looks like. All right, so what can you do with it? So let's talk about a couple of case studies, and then I'll sort of show you how to use it interactively, and then we can look at doing some hands-on if there's time. So the ExaWind project, which is part of ECP, is modeling wind turbines. And so what this figure from John Rood at the National Renewable Energy Laboratory is showing is it's showing the wakes of 3 wind turbines over time. And so as the blade spins, they're tracking the wake with a streamline, and then as the turbulent air moves, then these streamlines sort of break up and cause this disordered mess. And so what they're interested in measuring is not just a few individual turbines. They're actually interested in measuring entire wind farms on a mountaintop with interesting terrain. And so you have these streamlines for every one of these wind turbines. And so that's the problem that they're simulating. So what they did with Exowind on Frontier is they collected measurements on about 70,000 MPI ranks and about 8,000 GPUs for 17 minutes. And then using the HPC viewer user interface, they brought it up to look at the data. So this is a very complicated application. It's got one MPI rank. Exowind has one MPI rank accelerated with a GPU. And so that uses then 8 cores and the 8 GPU tiles on Frontier. And so that's using block structured AMR. And then on the remaining 56 cores, they're running Nalu Wind, which is using an unstructured mesh, and that's getting like finer resolution around the turbine hub and whatnot. And so what they're measuring here is this entire coupled application that's Nalu Wind and AMR Wind, which compose the Exowind application. And what this is showing is the MPI has been colored red here. And so all of the red here is waiting for MPI. And so there's a lot of wasted time in the application. And so when they talked about this with the Center of Excellence team at Oak Ridge and HPE folks, what they decided was that they were going to replace their non-blocking calls to send and receive with an I all-to-all V. So this is a non-blocking all-to-all call. And then they profiled the application again. And what this showed is that that basically all of the MPI wait time just sort of fell out. And so the application was a lot more efficient. So what John said was that they improved the performance on a large scale by 24x. And they were able to do that by understanding their code performance better by using HPCToolkit and running it on thousands of nodes while profiling. And something that should be of interest to you is that HPCToolkit could easily profile our entire application without a ton of instrumentation during the build process. So basically, you build the application the way you normally do, and then we're able to profile it on a large amount of Frontier and then map performance back to line numbers and loops and routines and visualize the traces. And so they were very pleased with what they were able to do with it. So this is an example where we were using HPCToolkit to look at the performance of lamps on Frontier before Frontier became generally available. And so this shows sort of 4 views of the performance. Let's look at each of these. So lamps is an application that is doing molecular dynamics, and for this particular run. And so what's happening is that every MPI rank is responsible for like a region in space and the atoms within, and then the atoms that are near the edge of your box are interacting with the atoms of your neighbor. And so you're continuously exchanging information with your neighbors in space. And so everybody's doing pretty much the same thing. They're working on a box of elements. And what we'd expect is this very sort of synchronous SPIMD behavior where there should be like a column where everybody's computing a little bit and then they communicate a little bit. And so what we see is that there's sort of this regular pattern where we see this blue stripe. I don't remember what the blue stripe is, but this is just like sort of part of their iterative behavior where every so many iterations they're doing something different. The interesting thing here is that we see this disorder creeping up here. And so it seems to happen reliably, sort of right after the blue activity, a few iterations later, we get some disorder. And so so what we're looking at here is only the work that's happening on the GPUs. We've hidden what's going on all the CPUs. And so we're just looking at the pattern of activity on the GPUs. So the green is for one kernel and the blue is for another kernel. And there's some other colors in here as well. And so this pattern of disorder here indicates that there's some kind of inefficiency that's causing delays. So when we looked and we zoomed in a little bit, And then we said, let's also reveal a couple of CPU trace lines. And so this is all postmortem where we're just like looking at the data. And in the viewer, you can reveal a few trace lines and then ask, what are the CPUs doing in this gap? And we find that that they're either executing MPI wait or MPI receive. And so then the question is, well, is this a cause or is this an effect? Is it because, are we delayed because we're waiting for communication, or is there something that's causing us to be delayed? And then if we're delayed, then we delay our neighbors. So we had a discussion with AMD, and they felt that it might be due to scratch space reclamation on the GPU. And so here's an interesting point. We said, so can we measure scratch space reclamation on the GPU? And they said, no, actually, they had no interface for measuring that. And since we're relying on the vendor interfaces for measuring our performance data, then we had to say, look, if you're doing things that can take arbitrary amounts of time or delay the application and delay its progress and perhaps cause delays that become visible in the overall execution, then you need to put something in your measurement API for that. And so they have. And so they now have a new profiling interface called Rock Profiler SDK that's still emerging, but it has some more measurement capabilities than we had at the time we collected this data. And so we were unable to ultimately deduce what the cause was, in part because we only got a few runs at scale before they took away our access to run things on the full scale of the machine. And so what we're looking at here is just a very small portion of the data. In fact, it's represented by like close to a single pixel in the minimap. So we have a lot of data here. I think we had a couple of terabytes of data, but we can look at it interactively with our user interface. So another thing that we can do is in our user interface, you can like bring up the top-down view and look at the call chain and then select something and then say, I want to graph. So here it says MPI send. I want to graph the time that each of the ranks was spending on MPI send. And so what we find is that, well, there's a whole bunch of GPU tiles that are not communicating. And then the CPUs are involved in MPI send. And you can see that there's this sweeping curve. So what we did is we sorted the time so that we would present the graph sorted in sorted order to show who's spending the most time. And for here, this is like somewhere under 50 seconds, and this is somewhere over 150 seconds. And so there's a difference about a factor of 3 in the time in MPI, and that all comes from the delays that we were looking at earlier. And so we actually think that that the communication is the problem. Well, it could be the GPU scratch space reclamation, but it is not imbalanced in the GPU work. The GPU work in the application is actually quite balanced. So that was showing, a sorted graph. We can also look at this as a histogram, and so you can see the distribution of where this is like the primary amount of time that everybody was waiting, but then there's a long tail and some of the ranks actually wait for as much as 3 times longer than everybody else. So this is interesting. This is an experiment where we're collecting it on 64K ranks, 8K nodes with 64K GPU tiles. And instead of launching the kernel with like millisecond times, my student made a mistake when trying to run a weak scaling experiment and didn't scale the work as he scaled the problems or as he scaled the node count. And so we ended up running kernels that were very short. And then we saw these bizarre effects where you can see that there's waves of waiting that are propagating, and then they kind of crash into each other and then cancel out. And so there's a whole lot of waiting going on. And so again, the question is, what's causing the waiting? Is it that since we're launching kernels so fast and completing them, that there's time spent for reclaiming the scratch space that in the GPUs that then causes waiting to propagate? Or are we spending our time waiting while there's congestion in the interconnect? And so that's something that we haven't gotten a handle on yet, but the tools show you that there are some significant problems in the system. All right, so let's take a look at a little more detailed look at games. So games is a an atomic, molecular, and electronic structure system. It does ab initio quantum chemistry, and it calculates energy, structures, and properties of a wide range of chemical systems. And so the data that we're going to look at here was collected at a prior Perlmutter hackathon. And so some of the data was on 4 CPUs and some of it was on 20 CPUs. I realize that we're about 40 minutes in and we haven't done any hands-on, but I think that what I want to give you a sense of is how you look at things with the user interface in order to understand your performance data, and then we'll either get to some of the hands-on closer to the end, or you have some time between now and the in-person hackathon or at the hackathon to work with my students. All right, so let's take a look at games. So when we bring up games, this was running on 4 ranks and 4 GPUs on Perlmutter. And when we open the trace view in the user interface, this is what we see. And so you're struck by this large amount of blue here. And the question is, what is that? Well, what we have is we've got MPI ranks. And so there's on the left, there's this band that shows that there's an alternation in color. And so this is showing there's like a light blue followed by a purple followed by a light blue. And so what that's showing is that this is a rank, and then this is another rank, and then this is another rank. And then the alternation between like the yellow and purple is showing different threads. And so, you know, we're rendering this at a scale that doesn't allow us to put like a legend next to it that says thread 0. But if you hover over one of these little blobs, it'll say, oh, this is on, you know, node 6, thread 7. Okay. And it will tell you exactly what it is, but we just don't want to allocate the real estate to have the text visible all the time. So what this blue is a whole bunch of threads that are actually they're OpenMP helper threads. And most of the time, they're just waiting for work. And then occasionally, you'll see that they become active and they actually do something other than sit in this blue, which just indicates a waiting color. Now, it's not that we chose waiting to be blue. It's just that the blue color is the color that was randomly assigned to the procedure that represents waiting in this this execution. And so this is, you know, waiting in NVIDIA's runtime system. So this is a GPU accelerated application. We have a GPU trace line here, so that the MPI rank, there's thread 0, there's a bunch of OpenMP helper threads, and then there's a trace line for the GPU. And so one thing we can do is we can pull up this filtering menu and say uncheck all. Like, I don't want to look at any of the things that are there. And then I can type in GPU for filter and then type check all. And now this is going to tell me to select only the GPU streams to look at. And, you know, let's suppress the CPU streams for now. So then here's the result. And so this is just showing only the GPU streams. There's 4 GPU streams, 1 for each of the GPUs on a, and this is, I'm sorry, there's 4 ranks and 4 GPUs. So it's all on one node in Perlmutter. And so we actually are seeing 4 GPU streams here. And now if we select a rectangle and zoom in a little bit, then this is what we see. And you can immediately see that there are some problems. And so you see these bands of color, and the bands of color indicate a procedure that is active on a GPU. And you can see that the amount of green work that's being done. So this actually is this kernel that they call their J06 kernel that performs some sort of calculation in their quantum chemistry code. And in fact, there's imbalance load inside their J06 kernel. And when we showed them this, they realized that actually they were taking a triangular iteration space and giving everybody the same number of rows. And so the further you get along the triangle, the longer the rows are, and that led to this load imbalance. And then there's a similar load imbalance here as well. And so some of the other things, some of their kernels are more balanced, but then they wanted to adjust this to get better load balance to avoid wasted waiting. So we can also look at this in the graphing view. that HPC viewer shows. So we select the frame that represents the J06 kernel in the call stack. And then we can see the amount of time on each of the GPUs is kind of like growing linearly, as one would expect by giving everyone an even number of rows in a triangular distribution. And then the rest of the things here, so these are a whole bunch of other threads, and they're not performing any. So the metric that we're looking at here is GPU operations. And so there's a whole bunch of execution contexts. They're CPU threads, and they're not performing GPU work. So in fact, the only thing that's performing GPU work are some of the execution contexts that are GPUs. And the red line here is not something that was done by HPC viewer. This is something that I overlaid on the figure just to sort of clarify what we're looking at on the slide. So now, so that was sort of like looking at things at the small scale on one node with a couple of GPUs that were all working together on the same computation. So now we're looking at 5 nodes, 40 ranks, 20 GPUs that are working on a larger problem. And so then we'll do the same thing where we'll filter out and just look at what's going on the GPUs. And we see a pattern like this. So now what we have is groups of 4 GPUs that are working on the same stuff, but each group of 4 is working on individual problems. And we can see that some of the groups of 4 are sort of starved for work and others are kind of overloaded for work. And so all this white here represents load imbalance. And so there's a major opportunity here if they can better balance the work among their groups of GPUs, then they'll get more performance out of it. And so another interesting thing here is that you can see in these columns of the pink. So this again is a kernel that's running on the GPU. You notice that there are these white gaps here, and so what that means is that the GPU is idle and something else is going on. And so this is after they rebalanced the work. They were able to get more better load balance, and we see that there's less idleness here than there was in the previous one, and we still have these gaps here. So if we want to isolate what's going on with the gaps, now this is looking at just all of the GPU streams. We can bring in a CPU stream, and then we want to see like what's going on the CPU while we have these gaps. So if we zoom in a bit, then in fact what we find is that there's an open BLAS routine that's being called. And so it turned out that they're doing a symmetric matrix multiply. They have a piece of code that was written in the late 70s, and it's using 2 calls to a sequential routine that is performing vector operations. And so what they could do instead of that is, in fact, call an OpenMP routine that's going to use multiple threads for the symmetric matrix multiply, and then spread out the work across the multiple OpenMP threads, the ones that were sitting in blue that were just idling there. And then by shortening this time, then you're getting then you're like reducing the amount of time between the GPU computations, so you're going to be more effectively using the GPU by keeping it less idle. So this just shows like looking at the piece of code, and there's the calls to DAXB, which is implemented by the open BLAS. And so they did replace this code. All right, so now let's look at another application. So this is a code called Quicksilver. So you can interactively explore the data for Quicksilver. I've loaded the data on Frontier, and you can use our user interface to look at it. You can also collect data for Quicksilver on Polaris. I have a set of tutorial examples where you can run the data collection as well as working with the user interface. So Quicksilver is a proxy application that explores some of the characteristics of Livermore's Mercury workload. It solves a dynamic Monte Carlo transport problem. It's written in MPI, OpenMP, and CUDA, and it has some load imbalance for the canned example. It's latency bound. It's got problems with table lookups. It's highly branchy, and it has poor vectorization. So one of the things we're able to do is using PC sampling, we're able to look in detail what's going on inside the kernel. So if I zoom in here, what you can see is there's a GPU kernel, and the application actually has pretty much one kernel. What they did is they took their sequential code, and then they decided that the best way to parallelize it was pretty much taking the entire code and putting it in a kernel, and then like launching millions of copies of that sequential code at the same time. And so by taking PC samples inside the GPU as it executes, we're attributing cost to the individual instructions. And then what we're doing post-mortem is we're taking the machine instructions and then say, okay, so this machine instruction is inside some function get reaction cross-section. And that is only called from macroscopic cross-section, which is only called from collision event. And so we're figuring out that if you're here, then we know how you got here. Now, it's not the case that you're going to have unique call chains for every function. You might call matrix multiply from several places in a kernel. But what we do is we have an approximation where we look at how much time you spent in a particular place. We look at how many calls you made to that particular function from the different places in the code, and then we proportionally divide up the time among the callers. We know that that's an approximation. It's something that's been done by gprof on CPUs since the 80s. And in the absence of better information with flat PC samples, that's all we can do. And so within a kernel, we can recover call chains, we can recover inline functions, we can recover loops, and attribute data down to individual lines. And so looking at the data for Quicksilver, what we found was that we're spending a lot of time on assertions, we're spending a lot of time on multi-level table lookups where it was indexing in a structure and then indexing in that and then indexing in that, about 5 levels of indexing for some of the inner kernels. And it turns out that some of the levels of indexing were constant for some of the loops that were surrounding it. And if the code were inline, then in fact you could do some of that indexing at an outer level and only do the inner 3 levels inside the loops. And my students showed that you could get about 20% better performance by rearranging the code in such way. So there are some resources on the web. So there's some documentation for HPCToolkit. There's a user manual. There's a cheat sheet on a wiki that basically shows how you use HPC run, HPC struct, HPC prof, and HPC viewer. There's a manual online for the viewer. There's some tutorial videos that can show, a full recorded demo that I recorded for supercomputing of like analysis of Quicksilver with HPC viewer. There's also a recorded tutorial presentation that gave a live demo analyzing games. You can download the software on your own systems, or you can use it on the systems at ALCF. So I'd be happy to take some questions now, and then we can look at how to use the user interface effectively and try some live examples. Any questions? All right, then let's look at some live data. Feel free to interrupt me with a question. You can just unmute and ask. I'm happy to do it that way. So let's shift over here. So this is on a node on Aurora. So on Aurora, I'm going to say module load, and this is in the slides. There's some material at the end of the slides. I'm going to say module load, soft, perf tools. Sorry, I want to say module use, soft, perf tools, HPCToolkit module files. And so this is where the HPCToolkit modules are. And then And this is, unfortunately, this is like not linked into the general module system. I'll get them to add that there. And then module load HPC toolkit. There are a couple of versions there. If I say module avail HPC toolkit, you'll see that there are a couple of versions that are available. One that I'm loading is a snapshot of our development branch. We're in the process of preparing for a new release. And so the last release was actually last year. There's been a bunch of stuff that's changed then, and so this is better. And so this is the default release. So if you just say module load HPC toolkit after setting up our module files, that's what you get. So the first thing we'll do is let's take a look at some of the performance data that I've loaded on the system. So here I'm running in an X11 VNC desktop that's running at Rice University, and I'm using a VNC viewer on my laptop. I could also use Samir's system through the browser, but I'll just use my virtual desktop out of habit. So I'll say HPC viewer. Flare. So there's paths to these things in the slides. So there's an HPC toolkit data directory, and then there's some different codes that have examples. And so for Quicksilver, there's two databases. And so we'll go look at the first. So one of them has profiles and traces, and the other has PC samples. So here I'll open this one up, which has the profiles and traces, because often I like to look at the traces first to see what's going on. So this is X11 running from a node on Aurora and back to my virtual desktop, and then the VNC viewer is rendering it on my laptop here. So we'll go look at the trace. So this was running on just 4 nodes, 4 GPUs. And so what we have here is we have the CPU trace lines are the ones that start with the green here, and then the GPU trace lines are the ones in between. So if we start out at the top level, it's like everything is in the program or things that the program calls. So main or things that main calls. So like everything is green. We've taken it all and like linked it up into these call chains, and so we can see it at like multiple levels of abstraction. And if I move down to level 2, then we can see that there's something here. This is initialized Monte Carlo, and then there's cycle tracking. And then if I click on the blue here, then that shows me that it's cycle init. So we're alternating between cycle init and cycle tracking, cycle init and cycle tracking. Okay. And then if I look at a deeper view, then I can just select over here and say, show me the deepest level in every call chain. So this is showing you where all of the data was really collected. And then, and so we're now looking at the bottom level, and we find out that there's time that's spent. So this color right here, this is time in MPI where we're performing an all reduce. Okay. And so you'll notice that there's more time that's spent in the all reduce on the first rank than on the last. And the reason is that the first rank is doing less GPU work and spending more time waiting for the synchronization with the others. And this one is spending more time doing the work. That'll become clearer if we go into this filter menu and say filter execution contexts. So now this says we're looking at everything. So I'll say, let's clear everything and then just focus on the GPUs. So I just type GPUs and then check all, and all it's doing is it's matching a string here. So I could have typed anything here, like I could have said context. It's whatever appears on the line. I'm just doing a string match on that, and then using that to just rapidly select the GPUs. So now we're focused on the GPUs, and this is showing just the trace lines for the GPUs. And if I zoom in, you can see that there's very significant load imbalance here. That the white color indicates no activity, which means that the GPU is idling. And so clearly this GPU is working, is doing a lot more work than the first GPU. And so if I were to look at this program and say, like, what's the problem? The problem is you should figure out how to better load balance your work if you want to get higher performance here. It's not about tuning your kernel. It's about load balancing your work. Okay. So there's a statistics pane over here. So on this pane here, I can select, and it shows that main is calling cycle tracking, which is launching a GPU kernel, and that's cycle tracking kernel. And so when we're just collecting things at the level of the individual GPU operations, then we can't see any detail inside the kernel. In fact, in the trace view, we don't show any detail like loops or source lines. We're just showing you the kernels, okay? We'd also show GPU operations. However, this application is using unified memory, and so all of the copies are implicit, and so those don't appear. Other things that we'll look at, the copies are explicit, where you're launching memory copies, and so then you'll see them. Now, if we go to the profile view and say, where are we spending our time? This is a very short execution. So if we go back and look at the trace and see how long was the execution, it ran for it ran for something like 5 seconds total. Okay, this is just a little simple benchmark. So if we go back into the profile and say, well, where did you actually spend your time? And we ask like where it's spent as real time, it's actually down inside CUDA Malloc managed was initially allocating the memory for the computation. About 59% of the total time was spent inside the memory allocator here. If I want to see where the GPU computation is done, we have, so this is, I had said monitor using real time, and then I said dash E GPU equals NVIDIA, and then it monitors a bunch of things. So we're monitoring GPU operations in general, but the GPU operations kernel launches are one kind of GPU operation. There's also memory copies. We have inclusive costs here, which is 100% of the GPU operations are in main or things main called. So that's inclusive costs. If we want to see where the things actually occurred, that's exclusive cost. That tells you stuff happened in this function. So what we can do from the top-down view is to sort by the GPU operations and say, let's sort by where we spent our time. And then I'll use this flame button and just move down the call chain and say, show me where it really happened. And it will open up the call chain and say there was a call to cycle tracking kernel, and 100% of the GPU operations were in cycle tracking kernel. The application only has one kernel, and all of the data copies are implicit using unified memory. Okay, so there's not too much to see here unless we actually go and look at the instruction level view with the PC sampling. So there, on other applications, there would also be columns that would show costs of data copies and like the cost in seconds and the amount of data that's being moved. There's nothing here because all the copies are implicit, so they're not being measured. But there's other data here that says like how much local memory you're using and how much fine-grained parallelism. And so so this has to do with how many threads there are, and then the fine-grained parallelism max is 64, and we're using 16 out of 64. The number of threads, there's 116 threads, and this says that there's 127 thread blocks. I'm sorry, 127 blocks. And the number of kernel executions that were launched, and then the occupancy. And so it says that we've got a 25% occupancy, which is what you would expect with the 16 out of 64. Okay, so let's look at the data for the PC sampling view where we're looking inside the kernel. So just go and say open database other, and I'll navigate to the other database. So from the, oops, I go to, let's see, I have to go out to, to flare. There we go. So flare, GPU hack. It's a little bit awkward when we're going sort of across the file system. Here we go. GPU hack, HPCToolkit, data, Quicksilver. Here's the PC sampling data. I'll open that. And so here, what this shows is now we're looking at this view where it's showing us inside the kernel. So the kernel is called, so we see the cycle tracking kernel, and there's a loop here in main where the cycle tracking kernel is called, and you'll notice that we're saying that the loop is associated with this source line. We're looking at the machine code, and we're identifying the source line that's associated with the loop as the one that the branch instruction in the loop maps back to. So sometimes it'll map to the start of the loop, sometimes it'll map to the end of the loop. It's just a question of what kind of attribution of the loops is done by the compiler. But once you understand that we're not looking at the source code, we're just like looking at the mappings, then things like mapping to the end of the loop makes sense. So we can see that in main, that there's a loop in main. And okay, again, it maps to the end of the loop. So here's our loop in main. And then on line 58, it calls cycle tracking. And so we can see both the call site at line 58. And if I select on the right-hand side, then it's going to take me to the function. And so this is taking me to the first line of the cycle tracking function. And that contains a loop at line 232. As we talked about, that's the loop shown here, which then calls cycle tracking guts. So cycle tracking kernel calls cycle tracking guts. And we've transitioned from the CPU into the GPU. And now looking inside the GPU, we can see that that cycle tracking kernel calls cycle tracking guts, calls an inline function, cycle tracking function. There's a loop inside this function. It's a do while loop. And so again, the line attribution is at the end of the loop. And then on line 63 in this function, it calls collision event. And so you can see this is the kind of profiling experience that you might expect on a CPU. And we're able to recover the same thing with this instruction level measurement capability on the GPU. So the columns that we have here indicate the instructions that are executed, the stalls that are incurred by the instructions. So these are stalls for any reason. And then we can look at, there's more stall reasons. So by default, we're just showing you this stalls for any reason. There's something here that allows you to select the metrics that you want to see. And you'll notice that there are a whole bunch of other things in here. They all say GINS for GPU instruction, STL for stall, and then this is a stall on dependencies between instructions. And so if I put my cursor over the top of any column, then in a moment, it's going to pop up and says, what this abbreviation means. So this is GPU instruction stalls for anything. And then this is GPU utilization based on computed using PC sampling. Okay, so you have the legend here, and you can also, by pulling up this menu, get access to all of the other metrics that are down there. And I can just say, okay, what I want to do is I want to take all this, I'm going to type a little expression to match. So basically I'm typing STL saying match all the metrics that have STL in it for all the stalls, and say check them all, and then make all of those columns appear. And then if I want to look at the reasons for the stalls, there's stalls for instruction fetch, stalls for instruction dependencies. And so keep in mind that what we're doing is we're getting this data from the hardware, from NVIDIA's hardware. And so we have the same kind of data that they get in Insight Compute. We're using the same, the CUPTI interface is doing the measurement for us as it does for Insight Compute. So we both have our ability to collect the same kind of data. The difference is that when we're doing this PC sampling here, we're coming up with estimates for GPU utilization and whatnot based on the PC sampling, and the utilization, like these metrics are done without all of the expensive replays that they do. So this enables us to actually use the PC sampling. You can measure things kind of in the large as opposed to really only doing it small scale and have it go very slow. Okay, so that gives you a sense of some of the things that you can do here. Let's look at another database. So I hope it offers the file chooser. Here we go. And we're back in our data directory. So this is Pele LMEX. This is a big database. This is going to take a moment to open. So this is a database from the hackathon. Notice I've got all of these opened in our user interface. So actually we have all the data in memory at the same time. This is from Pele low-mach simulations for exascale. I guess they're simulating combustion. I don't really know anything about the code. These are measurements that were taken by folks at NREL at a hackathon. So I'm bringing up the trace here. This is going to take a minute to come up. I have to actually check the size. I think it's actually a couple of gigabytes. We don't read the whole thing into the user interface. We are actually leaving the data on disk, and we're just sampling what is going to be displayed. So maybe there were a million things that happened over the course of time, and my window is only, say, 1,000 pixels wide, so I can only show at 1,000 points in time. So we don't try and summarize the whole thing. What we actually do is we say, well, I'm showing between times, say, 0 and 450, and I've got 1,000 pixels. And so then what I'm going to do is I'm going to look at 1,000 evenly spaced points and say, what are you doing at that point in time? And so we're sampling when we're measuring, but we're also sampling the measurement data when we present it in this user interface. As I mentioned, this database is a little larger, and the file system in Argonne isn't as fast as we'd like. So we've been able to actually bring up data for, it's not showing the main pane. I guess we're waiting for the data here. Is it blank? I looked at it earlier. It's not blank. So there's something that's going wrong with that X11 at the moment. So we've looked at data that's like 4 terabytes from lamps on Frontier, and it took about a minute or two to come up with the initial display, and then it took a few seconds, like maybe 30 seconds to switch the view, which is not as interactive as you'd like, but it was good enough for looking at something that was so big. Here we go. I'm not sure what happened with the initial rendering. So what this is showing is both CPU and GPU activity over time. And if we can zoom in and look, and you can see that these are like, iterations in the application. Okay, and if we select on something, this will show us the call stack for what's going on the CPU, and we can move up to a high level and try and get a sense of what's going on. So it's, I guess, advancing a time step, and so almost everything is this color, and then we see something else is going on in between. So this is do diagnostics, advanced time step. Okay. So the call chains give you this high level view of what's going on, so it makes it easier to understand. If we move down one more level, see what happens. Okay, now we see that there's a couple of more phases. So as part of advance, it's also doing velocity projections and diffuse velocity. So, and then there's something else going on here. It says compute differential diffusion. And so at this high level, we can look at the application at the different levels of abstraction and get a better sense of what's going on than if we look at it all the way down the bottom. So let's go and filter this and just look at the GPU activity. Now keep in mind, all of this data is on Aurora. And so if you bring up the user interface, you can look at this data as well. And so there's instructions at the end of the slides that tell you where the data is and how to load HPC Viewer. And so you can go and repeat the same thing that I'm doing or explore, as you see fit. Okay, so I'm going to uncheck everything, select the GPUs. And then re-render. Okay, go out to the home level. And then go down to the bottom and see what's going on. So one thing I want to mention that's actually really kind of important. So in the preferences, there's something that I have set here. And I'll show you the preferences in a second. So for traces, there's a setting that's clicked that says expose GPU traces. So what happens is a pixel on the display is representing some interval in time. And so we have, for every pixel, we have like a reference point in time, like to say the time at the left edge of the pixel is going to control everything that's being drawn in that pixel. And so whatever you were doing at the left edge is what we're going to show for that pixel. But it turns out that the GPU operations are often like launched and complete so quickly that there may be many things that are happening in the range of time that is being represented by a pixel. But at the point in time that I measured, the GPU may have been idle. And so you might just see a sea of white on the screen and not know where the GPU work is. Here, when we say expose GPU traces, instead of just saying, I'm going to paint the pixel white because at the left edge it was idle, we'll say, all right, at the left edge it was idle, but was there any GPU activity during the interval? And if so, I'm going to present the color for the first one. And so what this does is it tends to expose that there is GPU activity so that you know that, oh, there's something that's going on. And then I want to zoom in here to see what's going on instead of like looking at the sea of white and say, I need to figure out where to zoom to try and find the GPU activity. So this helps just show it. So if I turn this off and say, apply and close, I think the figure will probably get whiter. It should. May have to force it to re-render by just like reselecting the region.
John, I think someone is asking a question in the Slack channel. They're trying to install the HPCToolkit and they're having an issue.
You tried to install HPC Viewer on your laptop?
Can you unmute yourself and explain what's happening?
Okay. When I try and install the JDK with SPAC.
Yeah, yes.
Okay.
So it's on my, for my desktop.
Uh-huh.
So I follow the instructions. I install that with spec, and I set the path Java home. And then when I start HPC Viewer, I untarred that tar file. And when I start HPC Viewer, there is a pop-up that says, oh, there is a configuration error. And this file is pretty long, but I didn't want to have it all here.
Okay, so what kind of desktop are you installing this on?
On Ubuntu Linux.
Oh, on Ubuntu. So
Yeah.
then what you should do is you should just say spac install HPC viewer, which will install both OpenJDK and HPC viewer, and it will lash them together. And then you can just say spac load HPC viewer, and that will fix your path problems.
Oh, okay. So spec install HPC viewer. Okay.
Yes. And let it do the whole thing, and then it'll connect the two pieces, because it looks like it's starting with like Java 11 and it needs Java 17 or better.
So
Okay.
spec install HPC viewer. Okay, I'll try
Yes.
that. Thanks.
Okay. Excellent question. And this is in part why I didn't want to spend too much time on hands-on, because we'll spend all of our time talking about how to get X11 to show up on your laptop. And you know, it's a little more than like a 10-minute test to do that, to figure these things out for everybody. But I'm happy that you raised this question, because these are exactly the kinds of issues that come up. Okay. So I also wanted to just briefly demo, this is HPC viewer running on my laptop here. Okay, and what I'm doing here is I'm opening a remote database where I'm specifying that I want to go to Aurora, and there's a server that's installed on Aurora. HPC server is installed in the HPCToolkit directory. And so this is also captured at the end of the slides. And I'm using a password for authentication, because Aurora doesn't allow you to log in with SSH keys, as far as I know. So I'm going to use a password, and then I'll click OK. Now, here I'm already logged in. So let me just close some of these windows. So say close the database that's already on Aurora. And so I'll say open remote database. Okay, I guess it's memoized that, like, it's kept the thing open. But normally what it would do is it would pop up and it would give you the disclaimer that this is a federal system and don't expect any privacy, whatnot. You'll click OK, and then it'll prompt you for a password, and then you put in your password from MobilePass or a physical token in there, and then it came up in my home directory, pointing at all the things in my home directory. And so then I can just like go in here and go back to the same data that I was looking at before. Flare, GPU hack, HPCToolkit, data, games, look at their single group cholesterol simulation. So go look at the traces. So this is rendering traces directly from Aurora onto my laptop. No X11 involved, no browser-based server, no VNC desktop. This is our own communication protocol that we developed. We're working on improving the speed. Actually, the version running on the system does pretty well, as long as you've got a high-performance connection to the X11 desktop. This, I think, will ultimately be at least as fast, because we're getting X11 out of the way, which is sort of a chatty protocol that sends a lot of small messages and is very latency sensitive. And so what we're doing is we're shipping just the data that we're trying to render. Okay, so then I'm going to go up to this filter menu and then sort of do the same thing. So I'll just uncheck all and say, like, let's focus on the GPUs. And then we see this pattern, and then I'll say, let's move down the call chain. And then this is exactly what we saw in the slides, right? We see our load imbalance here in the J06 kernel, and we also see load imbalance in the J04 kernel. And then we can go into the profile view and expand this, looking for inclusive GPU operations, 100% here. So I'm going to go down the call chain to the GPU operations. And so what did it find? It found that there's this intermediate level that isn't a GPU operation itself. That's calling things. And so here's our kernel for the J16 kernel. And if I want to graph the GPU ops inclusive, I can plot them, and that shows me a plot of the GPU operations across the GPUs, and then there's a whole bunch of CPU, so rank 2 thread 8, rank 2 thread 9, those aren't performing GPU operations, those are the CPUs. And so this says rank 3 thread 0. So thread 0 is launching operations on the GPU. So the threads that are launching operations on the GPU are the ones that get the cost attributed to them. And there are other views here. So what I just said is plot the execution context, but I can plot a sorted graph. Okay, so now it's like all the low things are to the left, and then you see the sort, and that's showing us that in fact that there's this linear relationship of some kind. I can do a histogram plot. Okay, it shows that most of the operation, well, we saw that most of them aren't involved in it, but when you're involved, there's a couple of histogram buckets. Here it's sort of small and somewhat uninteresting. But this is actually an OpenMP program, and so these are OpenMP offloading using OpenMP target. And so we see down through from the program through to how the sausage is made through the runtime system, and the kernel pops out at the bottom. And so here's the kernel that has all of these OpenMP directives, and then there's the code that is subject to those directives. Okay. And then if we use PC sampling, then we get to see the detailed cost attribution inside the kernel. I have another example here that used the PC sampling on games. I think that's about the time I have today. There's just a couple of minutes. Be happy to answer a question or two, and then be happy to have myself or my team members interact with you over Slack as you try and use HPCToolkit on either the examples that we have here. So I'll just show you very briefly that there's the slides show that you can check out this tutorial examples repository. So I've already pre-checked it out. So this is from GitLab HPCToolkit tutorial examples. I also have a local mirror, but that doesn't matter here. And then for this tutorial, there's GPU, Intel, and then there's 3 examples, one that has OpenMP, one that has SYCL, one that is using Cocos on top of SYCL, and then the back is something that's local in my repository that was left over as I was preparing these last night. So if I go into the Minitest SYCL, then I can say, like, I've already got the data here, so I can just say source, setup env, Aurora, make clean, make very clean. We'll remove the build, and I can say make build, and it's configured. So in this case, it's like just a few source files that make a very simple application compiled with Intel's MPI compiler, and then make run. This launches something in the batch system, and it leaves a log file. It says, like, this is the log that says that something was launched. If I cat that file, it'll tell me what the launch was. And then, okay, it's launched in that job. And then as it runs, now I'm queued in the batch system. This is why I didn't do, a live demo. So what these examples are designed to do is you can say, if I say make here, it says there's some options. You can say make build, make run, make view, make clean, we'll just remove the data in the logs, and then make very clean will remove all the built code as well. And so that's in the SYCL example. The OpenMP example is just the same. It's like the same code. It's just that it's using OpenMP target to launch on the GPU to give you a sense of what that'll do. And so if I say make in here, then it says you've got, you know, the similar set of options. And then in ArborX, which is a Cocos example, this one, you do the same thing. You source the setup env aurora.sh, and then there are options here to say make build, make run. This shouldn't say PC sampling because we don't have that turned on in this architecture, but make run, make build, make view. This one will compile for a while because it'll build a complete copy of Cocos, and then it'll build the application on top of Cocos, and then you'll measure something that's a little bit more complicated. Okay,